All right, we've got a solid of revolution created by taking this little region of the plane. So this upper curve is y equals square root x, and then revolving around the line y equals 1, which it's a little bit hard to see the numbers on my graph. But y equals 1 is this dotted line right here. And we're going to slice this thing into disks, and we do that using disks that have the same symmetry axis as the shape that we're trying to represent. So I'm going to go like this. And there's a little slice of volume right there. And I've got to get the radius of the disk. So the distance between y equals 1 and y equals root x, and that's square root of x minus 1. Then my thickness is just a little bit of a dx there. Okay, now I can find the volume of one of these disks, and that differential contribution to volume I normally call dv. And that's going to be the area of the face of the disk, which is going to be pi times root x minus 1 all squared, multiplied by the thickness of the disk, which is dx. And so this is going pretty smoothly. I can just add these up with an integral. And I'll get the total volume of all the infinitely many infinitesimal disks all put together. So we're going from x equals 2 to x equals 3. So I'm going to expand what's inside the integrand, and I'll pull the pi out at the same time. So I have integral from 2 to 3. When I multiply square root of x times itself, I get just x. Well, maybe I'll just show this step. Right, squaring something means multiplying it by itself. So I'm multiplying that binomial by itself. So back to where I started talking. I take square root x and multiply it by itself, I get x. And then I get a negative square root of x and another negative square root of x. That's minus 2 root x. And then plus 1 dx. And every one of these can be done with the power rule. So I have 1/2 x to the 1/2. Oops. Let's see. There we go. 1/2 x squared. When I differentiate that, I get x. So we're cool. This other one I'm viewing as an x to the 1/2. And when I add 1 to the exponent, I get x to the 3/2 divided by 3/2, which is the same as multiplying by 2/3. And the last one gives me just an x. And then I evaluate that from x equals 2 to x equals 3. I'm going to continue over here to the left where I have a little more space, and I plug in my upper limit, and I get pi times the quantity 1/2 times 3 squared, which is 9, minus 4/3, because I combine the 2's over here, 3 to the 3/2, plus 3 minus pi times 1/2 2 squared, which is 4, minus 4/3 2 to the 3/2 plus a 2. I guess you could keep working on this thing for quite a while. I'm going to just go ahead and at least combine the terms that don't have the 3/2 power in them. So I have a 9/2 and a 3. 3 is 6/2, so that's 15/2. So pi times 15/2 minus 4/3, 3 to the 3/2. Let me think about this. So, because I should clean it up a little bit. 3 to the 3/2, that's the same as 3 times 3 to the 1/2. And so, again, because 3 is 3 to the 1. So I could write that as this term as 4/3 times 3 root 3. Maybe it cleans up a little better. The next term, I have a 2 out here. 1/2 of 4 plus another 2 gives me 4 total. And then I'll do the same thing with the 3/2 power. 2 to the 3 halves. So that's 2 times 2 to the 1 half. So 2 root 2. So I've got 15 halves pi, and then I have an 8 halves pi, negative 8 halves pi. So 15 minus 8 gives me 7 halves pi, or 7 pi over 4. And then my root 3 term is going to be minus 4 pi root 3. And then my root 2 term is going to be plus 8 pi over 3 root 2. Quick correction, I had 15 pi over 2 minus 8 pi over 2 from that term. So that's 7 pi over 2, not 4. And then I had, just to double check, negative 4 pi root 3. That looks good. And then I have a positive 8 pi over 3 root 2. So I think everything's good there.